Hello and welcome to the KIM-1 Corner Part 5. In this episode we'll be attempting to get this card working. Now this is a UART card, so we can take the load off the CPU so it doesn't have to do all its bit bashing to try and get the seal signal in and out, get this chip to do it all for us. But before we go anywhere, I need to modify this already. I thought of something I should have added first of all. So I'll pop that on and then we'll go through the datasheet, etc. of how this is meant to work. What I'm going to do is add another transistor up here that connects the transmitter buffer ready signal to the interrupt request line so that when this is empty, it tells the CPU it's okay to be used, and therefore we can at some stage create a buffer, and then this every so often just grabs the data out of the buffer and transmits it. Thus, the CPU doesn't hang around waiting for this to finish its previous transmission before going on to the next one. So for this quick modification on here, I've adjusted all the circuit board and the Gerber file, so I won't have to bodge it. But just for this, I shall bodge on here, if I can get it out, a 7002. There's a million MOSFETs you could use on here. It's just a little one, and I've got a bunch of them here. So this little general purpose MOSFET here, this is the same as ones I used on the CPU that I built, little N channel MOSFET, and one of them, oh there it goes, bit on the small side, and that does not look like a MOSFET. That's a 1M4148. I opened up the wrong tray. This one here, that's more like it. That's the last one as well on that strip. There we go, that transistor there. And we'll use a bit of this copper enamel wire. We only need two wires because this transistor we can solder onto this capacitor sitting just up here. Here we have the circuit diagram of this UART board. In the top left hand corner here we've got a 555 timer with just capacitor and resistor here, and potentiometer, so we can set an oscillator at 153.6 kilohertz, and that's 16 times 9600 baud. So that will give us our clock signal for our baud rate going into the 8251. So that signal there feeds into the transmit clock and around into the receive clock. So transmit and receive are at the same baud rate. And we have here our read data, and around this side transmit data, and these both just feed out to a USB to serial module. The same ones we used on the teletype port. This time it's feeding off this instead. We haven't got any circuitry for the current conversion. This is a direct connection. And we've got all the data lines coming in so we can put data in and out. And this has got two registers. We've got the data register and the control register. And we access them with the A0. So if there's a 0 on there, we're looking at data. And if it's a 1, we're looking at the control. So they're just one address apart. Now this address down here is just for one UART. I've got some jumpers down here so you can select different addresses and this will step up through the address range. This is just for the bottom one. Now for the write signal, that's fine. We've got a read write, which is 0 switching, but the read on here is a negative as well. So fortunately on our bus we've got a not read write. So I'm going to use that for the read signal, and that's the bit I'm a little bit worried about, whether the signals will be correct or not. Now over here, this is a bit I've just added, which is the transmit ready signal. Now that goes onto the gate of this MOSFET and onto the interrupt request signal. So we can switch the interrupt request down to 0 volts whenever this goes high, and we can use that as a signal to tell the processor that the buffer on this is empty if we ever enable it. Now further down here is a 74138 that's doing our address decoding. Now this is not a full decode because I just didn't have enough pins on it. I would have to put another chip on if I wanted to do a full decode, but I didn't think it was necessary really. So we're using the 0K5 signal, so when that goes low, so that's the same signal as what feeds to the riot chips. When that's low, it does that enable signal. When A9 is low, turns that one on. And when A8 is high, we get this one. So that's the main part of the address at the top. And then for the A, B and C signals, we've got A7, A6 and A5. We'll be using 32 addresses for each UART. We'll only be needing 2 of them. We'll be using 0 and 1, but we could use 2 and 3 or 4 and 5. The addresses will repeat up to make sure that any others we use jump above this. So if we connect onto this one, Y0, put a link across here, we'll be using these addresses here. And if we build another card and plug it in, we can put a link across this pin here and use the second output, and that will be 1520 to 153F, the address range of the next board. So you can plug in up to 8 boards if you so wished. Oh, moved the wrong one. But there's a clock on here as well. So the clock is just fed off the phase 2. It doesn't relate to the actual baud rate clock at all. It just has to be at least 4.5 times as fast as the baud rate to enable the internal workings of the UART to work. So we just use the phase 2 clock. And then there's the reset signal. So when the whole system's reset, it resets this chip as well. So what we need to do on this, first thing we need to do is set up this. So we need to power this board up and put the oscilloscope on here and see what frequency we're getting. Or we could use a multimeter with a frequency input to set this up, so you don't need an oscilloscope to do this bit. So let's transfer this over to the other side and we start configuring that. Now we need to power this up separately, and you can see the traces. So there's a trace going across from here, goes across the positive side of the capacitor over there. So that's our positive supply, and the next pin over is the negative, which we see runs around here and runs onto the negative side of that capacitor. So we can just put that jumper across there that I use for other balls we've had powered, and that'll be our supply. And then we can just power this up separately on its own and start measuring the frequency at that 555. Alright, I've connected up the board to the bench power supply. The supply coming in here, so it's just this board powered up. And now we're going to see if we can get the frequency 153.6 kilohertz. And we'll start twiddling. What have we got at the moment? Got so 223. If you look in the bottom right of the screen, you can see the frequency. See if we can get that bit nearer. Going the right way? Oh no, wrong way. Turn it the other way. 100 and nearly 152. Come back a bit. Well, we've got a fair bit of tolerance on this. Oh, there we go. 153.4. I think that'd be close enough. Let me know you need to be, if the other end is accurate, then we've got about 5% tolerance this end. But if we go for 2.5, so 2.5% would be about 4 kilohertz. Well, we're certainly within 4 kilohertz. Here we have the data sheet for the 8251. We'll be using it in a synchronous mode here. And we're using 8 bits. And the clock will be 16 times the baud rate. And we're using one stop bit at the end. And we should be able to reach 9600 baud in a sync mode. And that's why we need the 153.6 kilohertz signal, because 9600 times 16 is 153,600. Now here's the actual IC itself. Now on here we've got the data bus buffer, so that's for data coming in and out. And below that we've got a bunch of control logic. There's the reset signal, which is the same reset as what will be resetting the KIM-1 itself. And we've got a clock coming in here, which is the phase 2 clock. That just needs to be 4.5 times faster than the baud rate, and will be faster than that because that'd be 1 megahertz coming in there, so that's fine. And then you've got this C, not D. That's the control or data line. So if it's a 0, it's data. If it's a 1, it's a control signal. The control signal is so that we can tell the IC what to do, and the data is the data we actually want to send in and out. Now we've got this read and write signal as well, these two here. Now we've got a separate read-write, so it's read is when it's at 1 and write when it's at 0. Fortunately, on the edge connector of the KIM-1, we've also got a not read-write signal. So I'm going to use that for the read here and the normal read-write for the write. And hopefully that will work. If not, I'm going to have to build something else. Then here's our chip select signal, just to select it when we're in the right addressing range. Now here we've got this clear to send signal. That is tied to 0 volts because we need that tied down for this to be able to transmit any data. When you're transmitting, data from here will get transferred into the buffer over here and then clocked out using this TC signal. That's the clock signal baud rate generator. The 153.6 kilohertz will be feeding in there. Now the transistor I added earlier is coming off this pin here, so that says when the transmit buffer is empty or when it's ready to receive some data, that will come on and then I'll fed that through to the interrupt system. So at a later date we can build an interrupt controlled serial buffer into the KIM-1. Now down here we've got the receive side of things. We've got signals here that we could use for generating interrupts as well, but we need some sort of interrupt controller if we was to do that. So we won't be using that at the moment. And the data comes in here, gets clocked in, and what we'll do is when we want to see if there's anything needed, we'll just check this bit here. So this signal here, the receive ready status flag, you can read that internally as well to see whether there's a byte waiting to be read. So there's the clock input, which needs to be 4.5 times our baud rate in your synchronous mode. Now one of the things we've got to watch out for here is clear to send. A low on this input enables the 8251 to transmit data if the TX enable bit in the command byte is set to 1. So basically that bit needs to be turned on and that needs to be 0 to transmit anything. So that's tied to 0 volts, that's always 0. So we've got full control over just this bit in the command byte. Here is the calculation for working out what frequency you need for your baud rate generator, and it's just 16 times whatever baud rate you want. When you first start up, the control byte is in mode. You want a mode instruction put in there, and that controls the baud rate, the character length, whether it's 5, 6 or 7 bits, number of stop bits, whether it's synchronous or asynchronous, and your parity. And once that's been set up once, that input address then switches over. So you've got, it's first of all, it starts as a mode instruction. And then next time you access it is a command instruction on the same register. If you want to switch back to the mode instruction, you need to reset the chip, which we can do in the software. So that's okay. We look down at the actual instructions. This is the mode instruction here. And that consists of, we'll be putting on a 0, 1 here on these last 2 bits. Tell it it's 16 times the clock coming in. We'll be doing both of them on bits on for, we'll be doing 8-bit on those 2 bits. Then the parity bit, we'll leave that as 0. We'll disable it and it doesn't matter what, even or odd parity when it's disabled. And then these last 2 bits up here is to say how many stop bits you got. So we've got a 1 and a 0 there means stop bits. It doesn't show it here, but these bits here, if it's 0, 0, it actually puts into synchronous mode. So we won't want that one. We'll be wanting one of these 3. Once we set the mode, that address then becomes the command byte. And in that, you can set these various parts here. So we'll write to it again after we set the mode. And we've got, this is the transmit enable. So normally when you want to transmit, you'd put a byte in the data register and then turn this bit on and that'll enable it to transmit it. And then there's, we won't be using data terminal already. That will turn the DTR signal on and off on the output. Then there's this receive enable bit, which is a bit peculiar because this is the only place in the data sheet that this is mentioned. It doesn't say you need to have that on to enable receiving. That's something we need to investigate. And here's the internal reset. If we turn that bit on, which is this bit up here, we turn that on, then it will reset the whole chip. And we'll go back to mode, so we can set any change in stop bits, etc., which you shouldn't normally have to do. And hopefully we won't have to look at any of this stuff unless it doesn't work because of these read-write signals I'm not 100% certain of. So that's the data sheet. So we are back with the KIM-1, and we'll plug this in now. Just squeeze in. There we go. Right. And what I'll do is I'll plug this other lead I've got here into there. We have two comms ports on here now. We've got the one down here, which is what we normally be talking to it with. And now we've got the extra one, and we'll just see if we can send a bit of data out of that. So if we power this up, over current, over voltage, turn it on, press the reset, and let's see if we can talk to this. Okay, let's check what comms ports are on. So we're in COM 3 and 10. So if we open up PuTTY, and we do KIM-1, that'd be on COM 3 for the normal comms to it. Then we'll open up another one on COM 10 at 9600 baud. Now, COM 10 should be the new UART. Do a reset first, make sure everything's clear as it should be. Do it again. There we go, connected. So now we want to set the mode of the UART. That's on this page here. So we need to set these bits here. We went over a bit earlier. The top bits here for the number of stop bits. Well, there's 2 days between the last shot on this one. And we're going to go to 1.5 bits here, because there was all sorts of issues. So we're going to put a 1 and a 0 there. So we'll have 1, 0, 0. And those bits there be 1, 1 for 8 bits. And 16 would be 1, 0. So that would be 8E we need to send to start with. So bring it up here. So we go to address 1501, which is the command register. And we put in there 8E. And if we go back to that register, we now to tell it to enable the output. It's down here. And it's this byte here. We have to set it, the transmit to enable and the read to enable. So we definitely need to have to set this on, otherwise we don't receive anything. Although it doesn't actually say that in this document specifically. All the rest is 0. So that's 0, 5 we'll be sending to that. So we're on the command register, so we put 0, 5 and write that in. Now that should be the UART programmed up. So let's bring the screens up. So what we should be able to do now is put 1500 in, which is the data register. We put in 41, send that. Should get a letter A on the left hand screen. Ah, there we go. So that's working. So let's try 42 in there. Oh, we got letter B. Right. So the UART is transmitting. Let's see if it's receiving. So if we come over to there, so we're actually sending from the computer to the UART. We just press enter, which is carriage return, which is the number 13. And if we look at the data register, we've got 0D in there, which is 13. Let's double check it, give it another go. Press the A key this time. I've got caps lock on. Let's see what we got over here. See what we got on there. Go back there again. There we go, 41, which is 65 in decimal, which is ASCII for capital A. So we're receiving and transmitting. Several things I've learned in the last day is this register up here, this internal reset. When you start up, you don't know what status you're in. So you don't know whether you're setting the mode or just turning things on and off. When you're setting the mode, we'll be setting the stop and start bits. So if you're in the mode, you set that, then that's fine. But if you're actually running and you put that in, it does reset in, or vice versa. There's no way of telling which part of the register you're going to be writing to. So you don't even to that register or this one. And if you get them out of sync, it just doesn't work. There's no way of telling what mode you're in. So you just have to assume from reset you're in the correct mode. I also got the reset around the wrong way. It's negative instead of positive. So I've put a logic gate on so that when you press the reset on the processor, it actually resets the UART as well. So we can assume we're in this mode to start with, which seems to work quite reliably. I'll show the board what I've actually done to it. So here's the board with all the bodges on. And this transistor, I'll connect it up here so we could use the interrupt. I've had to disconnect it temporarily because as soon as this chip got enabled, it was creating an interrupt. Because it wasn't configured, it was crashing the KIM. So I've disconnected it. What I will do is I'll put a jumper on the new board so you can enable it, disable it easy. You may also notice that this capacitor's changed for the baud rate generator because my maths was a bit off and I worked out that it should have been a 200 nano when it should have been a 2.2 nano capacitor. So I had to change it. And you'll also notice there's a new IC up here. This is really bodged in. It's just a 4 NOR gates. So there's all the bodges on the back. Right mess. So what I'm doing here is two things. Getting the reset signal come in through this wire here. It's inverted and goes back out to the reset on the IC. So when we reset the KIM, it actually resets the UART as well. And the other one I've done over here, so I've used 2 of the NOR gates. Because the timing and write looked a bit iffy to me, and since the IC was installed anyhow, I took the not phase 2, it's not the phase 1 clock, it's actually an invert of the phase 2, the time is a bit different. And I got the right signal, and I ordered them and inverted them and sent you back into the right signal onto the UART. So the right signal is a shorter pulse, which is what this IC preferred. So phase 2 clock's giving us a nice pulse to get the timing a bit more accurately. So it now works better. So I shall make up a new board with the IC and transistors on, and so you can turn it on and off as you want it. So that is now working. So what I need to do now is get this to talk to the basic on, and I'd like to use this as the main board for talking to the KIM-1 with the monitor. So I need to change the monitor ROM to talk to these addresses rather than ones that are built in. And that will be in the next episode and a bit more involved. And that's just a software mod really. So we'll see if we can get that going. So there we go. That actually works now. You can talk to it. So don't forget to like and subscribe so you don't miss the next video where we make this the main connection to the KIM. That'll be running at 9600 and it will save a lot of time, make the processor or the whole thing run faster.